Welcome to Study Loop.
Okay, we need to talk about separation and purification. So, first, why is separation important? Well, let's imagine that you're doing a reaction. It doesn't matter if you're not familiar with this reaction, but suffice it to say, we can oxidize this with potassium permanganate. Followed with an aqueous acidic workup to get this molecule. Okay, formaldehyde. This is an organic molecule. It will dissolve in organic. Uh, sorry, will dissolve in organic solvents. Right. Um, but this also generates water, right? And this whole thing is in water. Uh, well, consider if the reason we made that molecule, okay? Imagine if the reason we made that molecule was so that we could do a further reaction on it with ethyl magnesium bromide, for example, because we wanted to generate this molecule, right? Well, it turns out that this reagent does not mix with water. If you have ethyl magnesium bromide with water, you end up just getting, uh, ethane and magnesium bromide hydroxide. It doesn't work. That's the point. Um, right? So sometimes you make a molecule, a new molecule, and you need to remove the water because you want to use a reagent that you can't use with water. That's an important part of separation, right? To remove things from water or remove things from solvents, right? Uh, why is purification important? Well, consider if we do a different reaction in which we get uh, a mixture of products, right? For example, if we had isopropyl bromide and we react this with sodium hydroxide, right, we're going to get isopropanol, but we're also going to get some propene, right? And we're also going to get sodium bromide salt, right, in either case, okay? And one of these will generate water, right? So we're going to have a bunch of stuff in our beaker, right? And if we only want one of them, to do a reaction with, then we're going to need to do separation. Okay, so that's why separation is important. What about purification? Well, let's consider if we're doing a type of reaction. Let's say we've made benzoic acid, for example. But let's say we've done it in such a way that we've also generated some sort of salt, perhaps sodium bromide. I don't know, right? Well, if we want just this benzoic acid, even if we can separate it, there's still going to be small, tiny amounts of sodium bromide left over that no matter how good your separation is, you can't get rid of, right? When you've got these essentially contaminant levels, like, parts per million, amounts of something left over that you can't get rid of in a separation, then you need to do a purification, usually a recrystallization, right? So we need purification to get pure products, right? Because sometimes, especially in the case of making medicines or, other syntheses, impurities can be disastrous, whether because it's going to interfere with a future step or simply because maybe it's dangerous when we're trying to make something that we can, ingest, right? Maybe we're doing pharmaceutical chemistry. Finally, what is a pure substance and how can it be identified? Typically, in the world of organic chemistry, a pure substance is just anything in which we don't have meaningful contaminants. And the way they're identified is that we do a melting point test. Right? So, pure substances have a sharp and distinct melting point. We'll say MP for melting point. If we test the melting point in a melt temp apparatus, and it doesn't match the literature or it's not sharp, then we don't have a pure substance, right? So typically, the way we test for pure substances is to melt the substance in a melt temp, melt the crystals in a melt temp, and see if it's a sharp melting point and if the melting point matches literature. Right, because impure substances, any impurities interfere with melting points. Slash melting points. Melting / melting points. Specifically, they depress